Hi, we're going to start talking about probability. Probability is a measure of the likelihood of events. A couple of definitions that we need to look at before we begin. The first is an experiment. An experiment is something with an uncertain result. And so some examples that we might have of an experiment are if we toss a coin, we don't know what we're going to get. If we roll a die, we don't know what we're going to get. And from a deck of cards, if we pick a card. Now, we talk about the outcome of an experiment, and that's the result of the experiment. So then we talk about a sample space, which is the set of all possible outcomes. How do you spell possible? Let's erase that. The set of all possible outcomes. Of an experiment. And so, for example, if I look at my coin, the sample space would be the set either heads or tails. If I look at my die, the sample space would be any of the numbers 1 through 6. And if I look at the cards, is everybody all right with the idea that there are 52 outcomes? 52 cards in that deck. An event is going to be defined as a subset of the sample space. And a favorable outcome to an event is an element of the event. And so if I put these two ideas together with my die, I could have the event be something like rolling an even number, and a favorable outcome could be any of the numbers 2, 4, or 6. Now, sometimes when we look at a sample space, it's drawn with a Venn diagram. And so if I try to picture a sample space that's drawn with a Venn diagram, and you might remember Venn diagrams from Math 108, I might have a class, and so my universal set would be the set of students. I might have one loop for students that are wearing jeans. I might have another loop for students that are wearing glasses. And so I might have some students that are just wearing jeans. I might have some students that are wearing both. I might have some students that are just wearing glasses. And then I might have some students that aren't wearing either. And so it's just a way of organizing that sample space. Now, we talk about a probability function, and a probability function is referred to, the authors of your textbook use the letter P, and it's a function of the sample space, so that each outcome X has a value P of X, and that value is between 0 and 1, and the total of the values is 1. So this part here tells me that probability is between 0 and 1. And this part tells me that the sum of the probabilities of for a sample space is 1. So your probabilities total to 1, and any individual probability will be a number between 0 and 1. The probability of an event is the sum of all of the probabilities of its favorable outcomes. And so, for example, when we looked at the die, if we looked at the probability of getting an even, that would equal the probability of getting that 2, plus the probability of getting that 4, plus the probability of getting that 6. Now, when we look at probability, there's a couple of different definitions of probability, and one is that of experimental probability. Experimental probability says that if an experiment is repeated n times and a certain outcome occurs r times, the experimental probability of that event is equal to r over n. So we could say that the experimental probability of an event is equal to the number of times the event occurs over the number of times the experiment was performed. And so, along with that idea, usually in class I hand out a penny to everybody, and I ask everybody to toss a coin once. So let's say instead we toss 10 coins. When I toss 10 coins, let's say we get 6 heads. Then we could say that the experimental probability of getting a head is 6 out of 10. And that takes us to something that we call the law of large numbers. And it says as the number of trials of an experiment increases, the experimental probability of the event approaches the fixed number. So we looked at 10 coins. If we looked at 100 coins or 1,000 coins or 1,000,000 coins, we find the more often that we did it, the closer that probability would get to an actual number that would be the exact probability of that event. So now, let's look at the idea of experimental probability from a data set. So for my data set here, I've got a list of grades on an exam. This was the results of, I believe this was the results of a 109 exam several semesters ago when I taught more than one section. And so the exam scores are what's given. What's the probability that a student scored in the 90s? Well, here, each student is an experiment. And so if I count, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 28, 29, 30, 31, 32, 33, 34, 35, 36 students. So the experiment is performed 36 times. My success is getting a score in the 90s, and that's 1, 2, 3, 4, 5, 6, 7. And so that experimental probability would be 7 out of 36. Now, in addition to the idea of experimental probability, we look at theoretical probability of an event in a sample space. And this is when each outcome is equally likely. If E is an event and N of E is the number of outcomes in the sample event, and N of S is the number of outcomes in the sample space, then the probability of the event is equal to the number of ways the event can occur over the number of outcomes in the sample space. And you might recall this notation from 108. This refers to the cardinality of a set, which means the number of elements in the set. And so what we're saying here is that the probability of an event is equal to the number of ways the event can occur over the number of outcomes in the sample space. And so if I roll a die, remember for our die, our sample space are the numbers 1 through 6. The probability of getting a 1 is 1 out of my 6 outcomes. The 2 is 1 out of my 6 outcomes. The 3 is 1 out of my 6 outcomes. The 4 is 1 out of my 6 outcomes. The 5 is 1 out of my 6 outcomes. The 6 is 1 out of my 6 outcomes. Those are my single events. And if I look at the sum of the probabilities, like we said before, 1, 6 plus 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 1, 6, the sum of all of those single probabilities will always add to 1. Over here, the probability of getting a 7 is 0. And we're going to say that that probability is 0 because the event is impossible. And if an event is impossible, its probability will be 0. Here, the probability of getting an even number, well, if I look at my sample space, there are 3 even numbers out of my 6 outcomes. Probability of getting an odd, if I look at my sample space, there are 3 odd numbers out of my 6 outcomes. Probability of getting a number less than 10. Less than 10, well, they're all less than 10, so that's 6 out of 6, or 1. And that's probability is 1 if the event is certain to occur. So putting these together, we're going to say that if the probability of an event is 0, it's impossible. If the probability of an event is 1, it's certain to occur. And so otherwise, probability will always be a number between 0 and 1, like we mentioned at the beginning. Now, next definition that we have are for mutually exclusive events. And now over here, technical definition, 2 events are mutually exclusive if their intersection sorry about that, let me try spelling that again. If their intersection is the empty set, or they have no outcomes in common. So, union, you might remember from your study of sets, is like the word or, and intersection, so this is union of two sets, corresponds to the word or, and the union is combining all the elements. And this next one, the intersection, of two sets corresponds to the word and it's the elements common to both. So if E and F are mutually exclusive, and again we said this meant that they have no outcomes in common, then we're going to say that the probability of E or F is equal to the probability of E plus the probability of F. So when I roll my die, the probability of getting a 3 or a 4, that's equal to the probability of getting a 3 plus the probability of getting a 4, or 1/6 plus 1/6, which gives me 2/6, which can reduce to 1/3. Another separate example, if I look at a deck of cards, what's the probability of picking a king or a queen? Well, that's equal to the probability of a king plus the probability of a queen. And there are 4 kings in my deck of the 52 cards. There are also 4 queens in my deck of the 52 cards. And so that adds to 8 over 52. I'm fine if you leave the answer not reduced, because we're looking at probability and not fractions. But if you do want to reduce that, that would, dividing out 4, give me 2/13. The probability of getting an ace or a jack, that would equal the probability of an ace plus the probability of a jack. And so ace, there's 4 out of 52. Jack, there's 4 out of 52. And so that again would give me 8 out of 52, or 2/13. Now this next one, if I want the probability of getting a queen or a heart, well, these are not exclusive. If I look at the queen of hearts, it's both a queen and a heart. And so here, that one card would be counted twice. And so if they're not mutually exclusive, the probability of E or F would equal the probability of E plus the probability of F minus the probability of E and F. Or, using the above example, the probability of a queen or a heart would equal the probability of a queen plus the probability of a heart minus the probability of a card that's both a queen and a heart, or my queen of hearts. And so queen, that's 4 out of 52. Hearts, that's 13 out of 52. But I've got that one card that was counted twice. And so here, when I add these, I get 16 out of 52. We sometimes talk about complementary events. If E is an event, E complement is its complement. And if they're complementary events, the probability of one is, the event is 1 minus the probability of its complement. And again, we're going back to set notation. And with set notation, if I have this be my set E, the complement is everything outside of it. So if two events are complementary, the probability of the event is 1 minus the probability of its complement. And complementary events we have nothing in common. But their sum makes up the entire sample space. So over here, if I ask, what's the probability of, let's say, not getting a jack when I pick 1 cards, that would be, the complement of that would be the probability of getting a jack. And so this would be 1 minus 4 out of 52, which would give me 48 out of 52. Now, in addition to talking about complementary events, sometimes we look at rolling 2 dice, instead of a single die. And when we look at rolling 2 die, we ask how many outcomes there are. Well, when I look at that, on the first die, there are 6 outcomes. On the second die, there are 6 outcomes. So there's 6 times 6, or 36 outcomes. So you might ask, how can it be that that gives me 36 outcomes? Well, if I were to try to draw it, if I let one die be 1, 2, 3, 4, 5, 6, the other die can be 1, 2, 3, 4, 5, 6. And so I could get a pair of 1s, I could get a 1 and a 2, I could get a 1 and a 3, I could get a 1 and a 4, a 1 and a 5, a 1 and a 6. I can get a 2 and a 1, 2 2s, a 2 and a 3, a 2 and a 4, a 2 and a 5, a 2 and a 6, 3, 1, 3, 2, and you get the idea. And so as we look at this list, we'll see that this arrangement has 36 sums. So what's the probability of getting a sum of at least 4? Well, that would be the probability of getting a sum of 4, or 5, or 6, or 7, or 8, or 9, or 10, or 11, or 12. wow, there would be a lot of things to figure out. Instead, if I look at the complement, that would be the probability of getting a 2 or a 3. Since those are complements, we can say the probability of getting at least 4 is 1 minus the probability of getting a 2 or a 3. And let's see, the probability of getting a 2, if I look at my arrangement, that's 1 out of 36, or means add. The probability of getting a 3 is 2 out of 36. So this gives me 1 minus 3 out of 36, which when I get a common denominator and subtract would give me 33 out of 36.